Some of the world's largest earthquake faults have remained quiet for decades or even centuries. That silence does not mean they are inactive. Along major subduction zones, tectonic plates continue to push against one another, steadily building stress beneath the oceans. These are the same boundaries that have produced the largest earthquakes and most destructive tsunamis in recorded history. Which of these giant faults is storing the greatest amount of strain? Which regions have gone the longest without a major rupture? Which coastlines face the greatest combination of earthquake and tsunami exposure? And why do some of the most dangerous places on Earth produce very few warning signs before a major event finally occurs? These questions have become increasingly important as scientists continue to improve their understanding of megathrust earthquakes. Modern satellite measurements, seafloor mapping, historical records, geological evidence, and tsunami deposits have revealed a crucial lesson. The absence of frequent earthquakes does not necessarily indicate reduced hazard. In some cases, the quietest sections of a subduction zone may be storing the greatest amount of energy. A megathrust forms where one tectonic plate is forced beneath another. This process, known as subduction, occurs along some of the longest fault systems on the planet. Unlike ordinary faults that may extend for tens or hundreds of kilometers, a megathrust can stretch for more than 1,000 kilometers, or more than 620 miles. When these immense fault surfaces rupture, they can generate earthquakes exceeding magnitude 9 and displace enormous volumes of seawater, producing destructive tsunamis that travel across entire ocean basins. The modern world has already witnessed the consequences. The Sumatra-Andaman earthquake of 2004 reached approximately magnitude 9.1 to 9.3 and produced a tsunami that affected countries across the Indian Ocean. The Tohoku earthquake of 2011 reached magnitude 9.0 and generated a tsunami that transformed large sections of northeastern Japan. Both events demonstrated that even advanced societies remain vulnerable when a megathrust releases centuries of accumulated strain. Yet neither Sumatra nor Tohoku appears among the highest-ranked concerns for future major ruptures today, because those sections have already released significant energy in recent decades. Attention instead focuses on regions where long intervals of relative quiet have persisted despite ongoing tectonic convergence. At the top of many hazard assessments sits the Cascadia subduction zone. Stretching from northern California through Oregon and Washington to southern British Columbia, Cascadia represents one of the most unusual major subduction systems on Earth. Unlike many active plate boundaries that produce frequent large earthquakes, Cascadia is remarkably quiet. The silence once led some researchers to question whether the region was capable of generating truly massive earthquakes at all. That assumption changed dramatically when evidence from multiple disciplines converged on the same conclusion. Coastal subsidence records, drowned forests, offshore sediment deposits, and historical tsunami accounts from Japan all pointed toward a colossal earthquake that occurred in the year 1700. Geological evidence indicates that a substantial portion of the margin ruptured nearly simultaneously, producing a massive tsunami that crossed the Pacific Ocean. More than 3 centuries have passed since that event. During that time, major population centers have expanded throughout the Pacific Northwest. Critical infrastructure, ports, bridges, energy facilities, communication networks, and transportation corridors now occupy regions that experienced little development during the centuries immediately following the last great earthquake. The concern surrounding Cascadia is not based on a belief that earthquakes follow a strict timetable. Earthquakes do not obey calendars. Instead, concern arises from the combination of a long, quiet interval, evidence of strong fault locking, and extensive exposure along the coastline. The same absence of frequent seismic activity that once appeared reassuring is now recognized as a possible indicator that large amounts of strain may still be accumulating. Across the Pacific Ocean lies another region that consistently ranks among the most closely watched megathrust systems: Japan's Nankai Trough. Running along the southern coast of Japan, the Nankai system has produced a long sequence of major earthquakes throughout recorded history. Historical accounts reveal repeated ruptures affecting different segments of the trough. Some earthquakes have broken individual sections, while others have involved multiple connected segments. The most recent major ruptures occurred during the mid-1940s. The Nankai earthquake struck in 1944, followed by the Nankai earthquake in 1946. Although these events released substantial energy, decades have now passed since those ruptures occurred. The Nankai region stands out because of the combination of extensive monitoring and dense population exposure. Few places on Earth possess such a concentration of infrastructure, industry, transportation systems, and urban development near an active megathrust boundary. Even moderate changes in hazard assessments attract significant attention because the potential consequences extend across some of the world's largest metropolitan and industrial regions. Farther southwest, the Manila Trench occupies a particularly significant position in discussions of future megathrust hazards. Extending west of the Philippines, this subduction zone has drawn increasing attention due to evidence suggesting substantial locking along portions of the plate boundary. Unlike some better-known megathrust systems, the Manila Trench has not produced a modern earthquake comparable to the most famous events of recent decades. That absence contributes to uncertainty. Historical records are incomplete, geological evidence remains challenging to interpret, and the full rupture potential of the system continues to be studied. The geographic setting amplifies concern. The South China Sea is surrounded by densely populated coastlines, major shipping routes, economic centers, and critical infrastructure. A large megathrust earthquake in this region would not affect only one nation. Tsunami waves generated within the basin could potentially impact multiple countries bordering the sea. Another major area of concern lies beneath the waters north of Puerto Rico. The Puerto Rico Trench marks the deepest part of the Atlantic Ocean and represents one of the most significant tectonic features in the Caribbean region. Historical evidence suggests that large earthquakes have occurred in the area, including a major event believed to have taken place during the late 18th century. Although the tectonic environment is complex, involving multiple interacting fault systems and plate boundaries, the trench remains a significant source of earthquake and tsunami hazard. Population growth throughout the Caribbean has increased exposure over time. Coastal development, tourism infrastructure, ports, transportation networks, and urban expansion mean that the consequences of a major offshore earthquake today would differ substantially from those experienced centuries ago. Moving into the southwest Pacific, New Zealand's Hikurangi subduction zone presents a fascinating and important case. Extending offshore from the eastern side of the North Island, Hikurangi exhibits a combination of behaviors that distinguish it from many other subduction systems. Researchers have observed slow slip events occurring along portions of the plate interface. During these episodes, sections of the fault move gradually over periods of days, weeks, or months instead of rupturing violently during an earthquake. Initially, some observers speculated that slow slip activity might reduce earthquake hazard by releasing accumulated strain. However, continued study has revealed a more complicated picture. Slow slip events do not necessarily eliminate the possibility of major earthquakes. Instead, they may coexist with strongly locked segments capable of generating large ruptures. Understanding how these different behaviors interact remains one of the most important challenges in modern earthquake science. The Lesser Antilles subduction zone forms another major arc of concern. Curving through the eastern Caribbean, the system extends near numerous islands that depend heavily on coastal infrastructure and maritime activity. Evidence indicates that significant strain may be accumulating along portions of the margin. Geological studies suggest that large earthquakes and tsunamis have occurred in the region during the past, although historical documentation remains incomplete for many older events. Hazard assessments increasingly emphasize that limited historical records do not necessarily imply limited earthquake potential. In many regions, written observations cover only a small fraction of the timescales over which megathrust earthquakes operate. Geological evidence often reveals events far larger or more frequent than historical records alone would suggest. Along the Pacific coast of Mexico lies one of the world's most famous seismic gaps, Guerrero. A seismic gap refers to a segment of a fault that has remained relatively quiet compared with adjacent sections. Such gaps attract attention because they may indicate areas where strain continues to accumulate. The Guerrero segment is especially interesting because it also experiences slow slip activity. Large portions of the fault periodically move without generating destructive earthquakes. Yet significant concern remains regarding the possibility that locked sections could still produce a major rupture. The Mexican subduction zone has generated numerous large earthquakes throughout history. Understanding which sections are releasing strain and which remain locked represents a critical challenge for hazard assessment. Indonesia's Sunda Arc has already produced some of the largest earthquakes ever recorded, particularly near Sumatra. However, attention increasingly focuses on the Java segment farther east. Compared with parts of Sumatra, portions of the Java margin have been relatively quiet historically. That difference does not imply reduced hazard. Instead, it raises questions about whether strain may be accumulating along sections that have not recently experienced major ruptures. Indonesia occupies one of the most tectonically active regions on Earth. The convergence of multiple plates, combined with dense coastal populations and extensive maritime activity, ensures that any significant megathrust earthquake would have regional implications extending far beyond the immediate rupture area. Across the Pacific, central Chile represents another area where long-term geological records are reshaping understanding of hazard. Chile has experienced many major earthquakes, including some of the largest ever documented. The magnitude 9.5 Valdivia earthquake of 1960 remains the strongest instrumentally recorded earthquake in history. Yet geological evidence suggests that the historical period may not fully represent the largest events possible along the Chilean margin. Some of the most extreme earthquakes and tsunamis may recur on timescales measured in centuries rather than decades. This realization has prompted renewed attention to sections of the margin that have not experienced the largest conceivable ruptures during the modern observational era. The challenge is not merely understanding what has happened recently, but recognizing what might occur over much longer timescales. Completing the list is the Alaska-Aleutian subduction zone, a vast tectonic system stretching across the northern Pacific. The region produced the famous 1964 Alaska earthquake, one of the largest earthquakes ever recorded, with a magnitude of approximately 9.2. However, the immense length of the Aleutian chain means that not all segments have ruptured in the same manner or at the same time. Some portions have experienced major earthquakes during the modern era, while others remain less well understood. Historical records become increasingly sparse farther back in time, making it difficult to determine exactly how individual segments behave over centuries. Despite Alaska's relatively low population density compared with some other regions on this list, the scale of the tectonic system ensures continued attention. Large earthquakes in the Aleutians can generate tsunamis affecting distant coastlines across the Pacific Ocean. One of the most important lessons emerging from the study of these 10 megathrust systems is that earthquake hazard cannot be judged solely by recent activity. Human intuition often associates danger with visible or frequent events. Yet megathrust earthquakes operate according to different rules. A boundary generating numerous small earthquakes may actually be releasing some strain incrementally. Another boundary that appears comparatively quiet may be storing energy for a much larger future rupture. Neither pattern guarantees a specific outcome, but both illustrate why earthquake forecasting remains extraordinarily difficult. The concept of a fault being overdue is particularly misleading. Earthquakes do not arrive according to fixed schedules. Recurrence intervals represent averages across many events rather than precise predictions. A fault that has exceeded its average recurrence interval may remain quiet for decades longer. Another may rupture sooner than expected. Consequently, hazard rankings focus less on predicting timing and more on evaluating conditions associated with large earthquakes. Long quiet intervals, evidence of strong locking, continued plate convergence, historical and geological records of major ruptures, and exposure of coastal populations all contribute to assessments of relative concern. Another key factor is tsunami generation. The most dangerous megathrust earthquakes often occur on shallow sections of the plate interface where significant vertical displacement reaches the seafloor. Even a few meters of sudden uplift or subsidence across a large area can displace enormous volumes of water. Tsunamis generated by megathrust earthquakes differ fundamentally from ordinary ocean waves. Their wavelengths can extend for hundreds of kilometers, allowing them to travel across entire ocean basins with relatively little energy loss. Coastal communities located thousands of kilometers from the source may still experience damaging impacts. Population growth has increased the stakes dramatically. Many coastal regions near these megathrust systems contain far more residents than they did during previous centuries. Ports, airports, industrial zones, energy infrastructure, communication systems, and transportation corridors concentrate enormous economic value within tsunami-prone areas. Urbanization has therefore transformed geological hazards into broader societal risks. The question is no longer limited to whether a fault can generate a major earthquake. It also encompasses how modern societies would respond to an event of that scale. Monitoring capabilities have improved enormously during recent decades. Satellites measure crustal deformation with remarkable precision. Ocean bottom instruments record subtle tectonic movements. Seismic networks detect earthquakes that would once have gone unnoticed. Tsunami warning systems provide increasingly rapid assessments. Even so, technology has not solved the central challenge. Scientists can identify areas accumulating strain, map locked fault segments, estimate potential rupture sizes, and evaluate probabilities. They cannot determine the exact day, month, or year when a major megathrust earthquake will occur. That uncertainty explains why the world's most concerning megathrusts remain under constant observation. Cascadia, Nankai, Manila, Puerto Rico, Hikurangi, Lesser Antilles, Guerrero, Java, Central Chile, and Alaska-Aleutian each represent unique geological systems with distinct histories and behaviors. Yet all share a common characteristic. They are capable of producing earthquakes large enough to reshape coastlines, alter landscapes, and affect millions of people. Centuries of apparent calm can create a powerful illusion of permanence. Coastal cities rise, generations pass, and memories of past disasters fade. Meanwhile, tectonic plates continue their relentless motion at rates measured in millimeters and centimeters per year. The movement appears insignificant on a human timescale, yet over decades and centuries it accumulates into forces capable of producing the largest earthquakes known on Earth. Among these 10 megathrust systems, no one can say which will move next. The planet offers no schedule and no countdown clock. The only certainty is that plate motion continues, strain continues to accumulate in locked regions, and the geological processes responsible for past megathrust earthquakes remain active today. For communities situated along vulnerable coastlines, that reality ensures that the world's quietest subduction zones may remain among its most closely watched places for decades to come. Another reason these 10 megathrust systems command so much attention is that the geological record repeatedly demonstrates how incomplete human memory can be. Even in regions with centuries of written history, the recurrence intervals of the largest earthquakes often exceed the lifespan of multiple generations. Entire societies can develop, expand, and transform during the quiet period between major ruptures. This creates a persistent challenge for hazard awareness. Communities naturally focus on events that have occurred within living memory. A coastline that has not experienced a devastating tsunami for several generations can begin to view such disasters as remote possibilities rather than realistic threats. Yet geological evidence preserved in coastal sediments, coral deposits, offshore landslide records, and tsunami sands often reveals a much longer history than historical documents alone. In many cases, researchers have discovered evidence of ancient tsunamis in places where no written account existed. Layers of marine sand found far inland have shown that powerful waves once reached locations considered safe by later generations. Similar discoveries have occurred around the Pacific Ocean, the Caribbean, and parts of the Indian Ocean. These findings reinforce a critical reality. The historical record is often only a brief snapshot of much longer tectonic cycles. The challenge becomes even greater when considering the immense size of some subduction zones. A megathrust does not always rupture in exactly the same way. One earthquake may break a relatively small section of a plate boundary, while another may rupture several connected segments simultaneously. This variability makes it difficult to compare past events directly with future possibilities. The 2004 Sumatra Andaman earthquake provided a striking example. The rupture propagated across approximately 1,300 kilometers, or roughly 808 miles, of fault length. Few scientists anticipated such an enormous rupture extent before the event occurred. The earthquake demonstrated that some megathrusts are capable of linking multiple segments into a single giant rupture under the right conditions. That lesson continues to influence assessments of many of today's most closely watched subduction zones. The question is often not simply whether a segment can generate a large earthquake, but whether multiple locked sections might fail together. Such a scenario can dramatically increase both earthquake magnitude and tsunami potential. Meanwhile, advances in monitoring technology continue to provide unprecedented views of these systems. High-precision satellite measurements can detect ground movements of just a few millimeters per year. Networks of ocean bottom seismometers are improving the ability to monitor offshore faults. New seafloor mapping projects are revealing geological structures that remained hidden for decades. Despite these improvements, one fact remains unchanged. No instrument can directly measure how close a megathrust is to failure. Scientists can identify accumulating strain, recognize locked regions, and estimate possible rupture scenarios, but the exact timing of an earthquake remains beyond current capabilities. That uncertainty is why preparedness remains the most practical response to megathrust hazards. Earthquake-resistant construction, tsunami evacuation planning, public education, and resilient infrastructure can reduce losses regardless of when the next major event occurs. These measures do not depend on predicting an earthquake. They depend on acknowledging that large earthquakes have happened before and will happen again. Among the 10 megathrust systems highlighted here, some may remain quiet for many decades. Others may produce significant earthquakes sooner. There is no reliable way to determine which fault will rupture next, yet all share the same underlying process. Tectonic plates continue to move, stress continues to accumulate, and the forces responsible for the greatest earthquakes in Earth's history remain active today. For that reason, the world's longest silent megathrusts are not merely geological curiosities. They represent some of the most consequential natural hazards on the planet, capable of affecting coastlines, economies, and populations on a scale few other natural processes can match. Their silence may persist for years or centuries more, but it is the continuing accumulation of strain during those quiet intervals that keeps them at the center of global earthquake risk assessments.